the average distance from here is smaller than where you live is smaller than normal. I don't think people from Rotterdam made it as much as others. So I completely understand. If you speak to people, I will try to make the slides of today's lecture online available as early as possible, so that people who didn't decide not to come today would still have the material. There are two important topics today, and that is really an algorithm for finding the right models for doing some learning. And the other one is on feature selection, or on how to deal with features in a machine learning process, which is very important for your practical assignment as well. So these are the two main topics that one in the first half, the second one in the second half. But I still want to go on a little bit with the systematic approach to introducing some ideas of machine learning. And there, I think an important thing is to also take into account a third kind of learning. So we have seen, we will see later the learning by, I would call it model selection, or yeah, probably that's a good word. So finding the best model for your classification problem or your regression problem. We've seen yesterday the probabilistic approach with the Bayesian, where you just estimate the probability of a certain class being true given a set of features. And the surprising thing is that if you use a relatively naive approach of just using Bayesian networks for predicting your probabilities, assuming independence of your features, that you can still get a pretty accurate prediction algorithm. So that was the second one. And today we have what's called sometimes a lazy learning algorithm. That's one where you don't build a model up front, but where you decide classes by comparing to other already classified objects. So you don't build a model up front, but in a way you look at what you've already seen, and you decide on classifying according to the instances that you have already seen in your approach. And the algorithms for doing that are usually sort of the basic idea is what's called k nearest neighbor learning. And I will give the example for classification, because that's where that fits more our line, but you can use this algorithm also very nicely for clustering. So we use it now for classification, and the idea is let's go back again to our feature space, where we just have some dimension attribute 1 and another dimension, and we have a classification of 5 blue and 5 red, let it be male or female or whatever you want, spam or not spam, and then you get a new object, the pink one. And the question is now, what would be your expectation? Would it be a blue one or a red one? And I think everybody would think, just by even without knowing any details, what is the problem and so forth, that given this feature space, we would expect this pink one to be red. Yeah? So it is, because it's so close to the other red ones and so far away from the blue ones, which means in our feature space representation that it shares the features with the red ones more than it shares the features with the blue one. And that's why you would expect this to be classified as a red node. So basically how you do that in a more mathematical way is that you just look at the distance between the nearest neighbor, and you give your object, your instance, the class of the nearest neighbor. Yeah, so that's the very simple version of this algorithm, is you just assign the value of the nearest neighbor. But obviously there is if you always use this very naive approach, then you are very much dependent on some noise in your data. And you can make classification worse, of course. If you classify one instance badly, incorrectly, then the next one will use this instance for learning. So it's very important to have the right classification in this process. So let's look at it in a little bit more detail. So the task is to classify a new object when it comes, according to, in this case, 3 categories. So we have the category government, science, and arts. And we have some features, could be a text or whatever. And then the question of what I just explained, the algorithm would be find the most similar one according to the similarity relation defined by our attribute set, and just assign the label of this. So that should, in principle, work pretty easily, pretty well, if you don't have any mistakes, and if you have objects that are not sort of located directly on one of those lines. So when we find this new object, this new document, for example, then all we have to do is to look at the nearest neighbor. That would be the original algorithm, and then you would assign the value red for government to this, and you're done. So the problem is that you have noise, you have always mistakes in your training data, or you have exceptions, could all be. So for example, here you have this green one, which has been either misclassified or is really a document about science, but sort of has other properties. So it's the exception in this case. And if you now find an object that you want to classify, which is very close to this one by coincidence, then you will give it the wrong. If you just have the nearest neighbor approach, then you will give it the wrong class as well. So instead of doing this, what the k-nearest neighbor does, as you might have already guessed from the name of the algorithm, is that you don't just look at the first, the closest one, but that you take a number of, for example, three nearest neighbor, and you check at these three nearest neighbors what is the majority of the classes. And then if you have a 3 nearest neighbor algorithm in this case, you would assign the red one to this. It's a very simple method, and obviously you need to find the right parameter for k. That depends on the number, on the level of noise that you have, and this allows you to write a very simple algorithm by just looking at the instances that have already been classified. So, and that would give you the probably right classification here, that this is also a document about government as all the objects around it, with the exception of the green one, are. So then the algorithm is in intuitive terms, is the following. You just find the k most similar cases, and you assign the label of the majority. So that's in principle all I wanted to tell you about this alternative method for learning, for classification. And I think that the core is, it's a nice idea. It's very simple to implement, and it's very efficient in many cases. But there is a fundamental difference in learning methodology. And I think that's why this is so important to have seen once. And of course, when you apply it, you have to read about all the details. So how do you define the similarity and so forth? Is majority always the best one, or are there maybe better ways of deciding in the end? So this is just the global idea of this algorithm. But there is this one distinction between lazy learning and eager learning. And that is that in this case, we don't have to go through the training examples that we already have and build a model. So have some calculation of, for example, a line or a hyperplane or whatever you would like to have as a representative model. But that the only thing you have to do is you go through the list. When you find a new instance, you go through your list and you search for the most similar ones. So there is no model construction in the beginning of your algorithm. Yeah, so that's a different class of algorithms that do not construct a model based on previously seen data. And here, you need to have access to the data itself in order to do the classification. Whereas if you have your training, you build your model, and then you can throw away your data. You don't need your data anymore. So these are fundamental differences. For example, if you think about privacy questions, then you could say, I train a model on some data that I don't want to give the data out. I train my model, and then I ship the model without the data. And this is a different case than if you say, okay, here's the data set, do your k-nearest neighbor. Although one has to be careful that if you have a model and it predicts based on some data that you don't want to get out, you have to be sure that your model can't reproduce the data in the first place, so that you anonymize it still and that it doesn't reproduce names and addresses and this kind of stuff that you don't want to share, but just keeps the features that are necessary for classification and so forth for new data that are unknown so far. But it's this fundamental difference that you need to understand between something that builds an explicit model that you can ship without the data, or something that doesn't need a model, but then you need the data in order to do predictions. Okay, so that was a sort of a sidestep before we now move into the main topic of today, the thing that really are most important for you to know for the final assignment, for the third bot that you have, third week bot that you have to write for the third module. And also, I would say, for understanding the main approaches to learning nowadays. So how is modern learning the last years, how does that work? What is the novelty of deep learning and neural network learning? This is something that Peter is going to talk about tomorrow. But that is just a specific case of the general method that I'm going to talk about now. Yeah? And question is, how do we find appropriate models based on some feature spaces? And we are looking here at some binary classification. Remember, we had it yesterday. You have some data, previously seen data. It has been classified either as SPAN or HAM. And now the question is, can you build a model that decides automatically whether some new and unseen data belongs to the one class or the other? That's the simple task that we want to address. And this is the data set from yesterday that we've seen, where we more looked at finding a curve. This is the same data set now with some age and some height and some class, whether it's male or female. And the model, what I referred to as a model, would be the choice of a specific mathematical tool, and that is a line in this case. So a linear classifier would just draw a line in our space and say everything that's above this line would belong to the first class, everything that's below the line would belong to the other class. And if we have our examples, the male ones in blue and the red ones in red, and you write this classifier, then you see that it's not bad. It classifies most of the examples correctly. There's quite a lot of noise in the middle. So there are many red ones here, and there are many blue ones down here. And in particular, if you look at this downside, then this is very sort of going wrong. So there are algorithms to find such a line, and I will show these algorithms in a minute. But there's also some very old experience and knowledge about this problem, which is showing that there's data sets where you will never be able to find such a linear classifier. And an example for such data sets are those where you have some logical operators. So here is a problem of representing the logical statement of disjunction. And it's a propositional logic disjunction, so it is has the meaning that this is true if either y is true or p or x is true or both. Yeah. So if we give the value 1 for truth and 0 for falsity, then this would be a representation of the data set of the logical operator disjunction. Yeah. And then it is clear that if we just have a line that distinguishes between these 3 points and the 0, then we have found a classifier, a linear classifier, to decide whether something is true according to this formula or not. Oops, that was too fast. But then there's the operator XOR, which is true if one of them is true but not both. Yeah, so if y is true, then the formula is true. If x is true but not y, then the formula is true. And in the two other cases, it's not. And no matter how you try your best to draw a line through those in the space, you will never be able to find a line that distinguishes between the red and the circles. And that was a result from, I think, 40 years ago, that there is a way of representing propositional logic, reasoning and learning this using neural networks. And these neural networks, these very simple structures of neural networks, were able to find linear classifiers. And the negative result at the time was that those things can learn specific logical operators, such as OR, but they will never be able to learn others, such as the exclusive OR. Yeah, so that's a result that goes back quite a long time, and it shows you that not for all problems and not for all data, you will be able to find linear classifiers. And that is a more theoretical result, and an intuition behind it. And this is sort of a practical result which you can sort of more intuitively, I think, relate to, that if this is the way as you specify it, and you have someone who is very young, then these people are very small, and then you can't just draw a line between the male and the female people, maybe in the more standard average range of age, but not in the outer sides. So I've shown you this example for two features, two attributes. The attributes age, sorry, this is age, this was height. And then the task of linear classification or classification is to draw a line between the two classes. This also works for all the other dimensions, of course. So this is not an approach that only is restricted to the two-dimensional case. If you have a one-dimensional case, so if you only have age and you want to classify between the old people and the young people, and we have a class, then the classifier is only a point, a data point. So everybody, if I would ask you what is your definition of age, someone who's old or someone who's not old, then probably there would be a data point somewhere where above 75, I would have learned that you think above 75 it's old and beyond it's not old. So the classification in the one-dimensional case is just a point in this feature space. In the two-dimensional, it's a line. In the three-dimensional, we can still sort of visualize it as a hyperplane. So this is a three-dimensional space, and this would be the sort of the plane that cuts in the middle of this. And then the object of one class would be in the one half, the other one's in the other half. And obviously, if we move to the fourth dimension, our sort of geometrical imagination stops to seeing how that works. But fortunately, the mathematics behind it work exactly the same way as for the three-dimensional and the two-dimensional case. Basically, what the task then is, if you have, for example, this more complex case, then you just have to come up with a hyperplane in this five-dimensional space, or the four-dimensional space this is. Yeah. For the sake of simplicity, we'll always stay in two-dimensional space here. But as I said, this is sort of, the rest is mathematics. So that was the question of linear separability in the first case, and the idea of what would be a good separator, so a point or a line or a hyperplane. But even if you restrict it to a line, if you know that what you're looking for is a line to separate, a linear separator, you still have the question that there might be more lines that could separate your data in a good way. Yeah? If you have to choose a hyperplane here, which one would you choose given this training data? And that is basically what we're going to look into now, or in the second half. What are good algorithms for choosing the right hyperplane? So we've chosen the model. The model is the hyperplane. because this is easy to calculate with, and it's very powerful, and I will show you that this can even cover very complex cases of data. So the choice of the model is a line or a hyperplane. And now the question is, how can we find the optimal one given some data in our data sets? And then one of the notions that's underlying the very successful systems from 10 years ago, I think the most successful systems were called the support vector machines, as some of you probably have heard. And they are basically based on this idea that you look for hyperplane, the green one, that has the biggest margin of parallel hyperplanes around it that still split the data. So you see, as soon as you change the angle here, then you would lose this blue one, for example, if you would turn the angle like this. And then the whole problem becomes basically an optimization problem for how can I find the best hyperplanes that have the property of minimizing the distance of the blue ones from this line and the red one from the other one. So I won't go into details of this algorithm. It's just a sort of a mathematical formula that describes exactly the property of maximizing these distances or minimizing the distance. I don't know the detail. We see a different approach tomorrow with the neural networks that does this very similar thing. But that's the general idea. You have an optimization of a mathematical formula, so you need the vector representation of the data, and this vector representation of the data describes the error margin or distances between your prediction and the lines. You also have to take care of the exceptions, so you also have to sort of minimize the ones that would be on the wrong side of your hyperplane, and then you get a mathematical formula that you just have to fill in with your data, and you have to optimize it, and that gives you then the perfect hyperplane. So still this is under the assumption that we work with hyperplanes. And as I showed you this example before, we're limited by the data that we have here. Because the best hyperplane that you can find here, or line that you can find here, still will exclude many of the blue ones here in the middle and the red ones above the line. So in a way, we are limited very much by just the choice of this one model class. And that was what, so I'm not an expert in machine learning. I know a little bit, but I'm not an expert, I have to admit. But this was, for me, one of the eye-openers. And I think that's the one thing which you can play around with in your project and this week as well, that these models are still extremely powerful because we can do something with the data. And what we can do with the data is called a design matrix. So the design matrix is a very, very simple trick by just extending the data set that we have with more features. And these more features are not sort of random features we add, but they are properties that we add based on the data that we have already in our data set. And basically the idea is that if we have the age and the height as features in our data set, that's the first two columns are the table that we've seen before. We can simply add a column a square, for example. Nothing changes in the data. It's valid data. If in logical terms, it would say this data is entailed by the data that we already have. And basically, you just add this to your table. And you also add the square of the height, and you add the square of the, or no, not the square, but the multiplication of the two values for the two features. So basically, we have now turned this two-dimensional data set into a five-dimensional data set. And the brilliant thing is now that given with this data set, we can use a linear classifier in this five-dimensional space that allows us to separate these classes pretty well. Yeah? So basically, if you now draw this, this hyperplane in a 5-dimensional space, your hyperplane suddenly does this separation. Or in a graphical way, thinking in a more graphical way in another example, suppose that we have this space where we have all those red lines in the middle, the red points in the middle, and the blue ones around. Then, as you will see, there is no linear separation. Yeah. So, with the linear model, we will never be able to find a linear separator, a good hyperplane that separates positive and the negative examples, if we just use this feature space. But if we now add to the feature space the information x squared plus y squared, which gives us a third dimension, suddenly all the ones in the middle, in this middle circle, remain on the bottom of the 3-dimensional space, and the blue ones go to the top of the 3-dimensional space. Because basically, this line, this circle, gives you the distance from the 0 point. And if you add that as a dimension, then you get the distance to the 0 point, and basically, suddenly, we have a linear classifier here. We have the hyperplane that we can just add here. So that's very powerful. So we didn't add anything, we didn't have any magic, but we just represented the data with some extra information in a different feature space, and we have found the classifier. So now what you even can do is that you say we have the information x and y, the values for x and y, so this, but now we build a different feature space, a different design matrix, in which you only plot x squared and y squared. So leave out the a and the y, the x and the y, and then you get suddenly this feature space, where on the y square x you have this is the y-axis, you have the y square, and here you have the x square, and suddenly all the red ones are in the corner close to the 0, and the blue ones on the outside. So we've gone back from this 3-dimensional feature space to the 2-dimensional feature space. So with exactly the same data, we've now built 3 different feature spaces, design matrices, and these give us now 2 different linear separations for the same data. So without changing the model itself, we can still look for linear classifiers, as simple as possible, Occam's razor from yesterday. Try to find a simple representation for your model, because these are very often very robust against exceptions and noise. Find the simplest model, and the only thing we did was to change the data so that we could still use the same simple model. So I thought that was, yeah.
In this method, do you throw away information? Because in the last, in the bottom right, you lose all the information for positive or negative.
Yeah, so in this case, you don't lose information if you just add a feature to your design matrix. You don't lose anything. So this is contains the same information. But now it makes it easier for your learning method to find the right model, or possible in the first place. But it is a choice. This is obviously far more expensive to calculate a model on, because now you need to you need to optimize your hyperplane according to 5 features in a 5-dimensional space. So you might choose in your practical assignment to say, okay, I throw away some of the information, because the chances that I find a model in this feature space are high, and then it still will give you a very good classification. Yeah, and that's, I think, something very powerful you can use when you do the Schnapsen intelligent agent, because there will be some very simple features to calculate to get out of your game, and then that might not be powerful enough to give you a good linear classifier. So you might change your matrix to a design matrix so that you have more chances, more dimensions, and in this dimension you might find a linear classifier. Yeah?
Do you only use these features for classification, or would you also use it for clustering? Would you be able to?
The question was whether you would only use these features for classification or also for clustering. The answer is I do not know, but that if I was to give you an educated guess, I would say that you can also use them for clustering.
So it doesn't really matter if it's supervised or
I don't think it matters, because in a way, if you look at this this example again, then it would make a lot of sense to cluster those elements here and cluster those elements here, and it might be more difficult to cluster them in this rather than in this, because they might be in a more distant region from the other examples rather than in this representation. So my guess, as I say, would be that this also is very useful for clustering. But I have no experience with that. Yeah? So we'll have a look later today to the question of how can we use machine learning for improving our intelligent agents. We'll look at that in the second half, I believe, or later. But that's really a very powerful means for you to play around with different machine learning methods. Because you have just one machine learning method that finds the optimal hyperplane. So that's your neural network or a support vector machine or whatever you want to use. But then and you use that off the shelf, so you're not going to build your own machine learning machine that finds the models. But for your data, you can think of, oh, yeah, what might be able to help me here? So just build a design matrix that combines the information you have in your original feature set. And that is, I think, something very interesting to play around with and see what the impact of this choice of design, of the features, has on the performance in the game. I want to come back to the support vector machines, just to give you some sort of ideas of what the power of these support vector machines is. I told you that there is a mathematical formula to find the optimal hyperplanes by the distance between the lines and the instances in the set. But if you do the mathematical calculation behind that optimization, it turns out that this only depends on local properties between instances themselves. So it has been shown that I can find the optimal hyperplane by just calculating the distance between individual objects in my space. And depending on how I represent my space then, I can, again, calculate this optimal hyperplane and find a good one. But the only thing I need is to take two instances, compare them, and then calculate this for all the instances and pairwise. And that is called a kernel trick, because this helps you to find in an extra dimension locally the optimal classifier. So in a way, intuitively speaking, your clustering, your algorithm for finding the right hyperplane would be very precisely tuned to exactly the instances you have in your data set. So you think of this as a three-dimensional space where all the objects in blue are now one level higher, and you can cut over all of them directly. There are various methods for calculating the distances of these objects that allow you to do exactly this. So this has been a very, very powerful method, and it gives very precise hyperplane. But the problem with this approach is that it's not very robust. So it is very easy that you can overfit, as this is called. So overfitting your model towards your data, because it finds all these nice little spots. But suppose there would be a new thing here, which one is it supposed to now take? So the problem with these very precise and very elegant methods, these kernel methods in support vector machines, is that you can build them so well that they are so tuned to your data that they don't work on new data because it's sort of too much already trained on the data, which is called overfitting. So support vector machines are, if they use this kernel trait, then what you have to take care of is mostly dealing with this overfitting. And there are methods that you leave out a lot of data, so this has been researched on this. How do you deal with this problem specifically? So before we have a break, I want to spend a little bit of time now how we can translate this to Schnapsen. And for that, I want to tell you a little bit how AlphaGo was implemented, because in principle our problem is in a way similar to the Go problem. It has some different properties, and that also means that we need to look at it in a slightly different way. But it's quite interesting to compare the things. And of course, we need to sort of go back to min-max, because that's also on the basis of this algorithm. And so, of course, we have the phase 2. When we have the phase 2, we can apply min-max. Alpha-beta pruning is very efficient. We can, in principle, always find a winning strategy in the phase 2. Whenever there is one, we're done. Yeah? So phase 2 is a solved problem with the material we have from the first week. Problem is, what do we do when we have phase 1? Phase 1, as I said, we have these belief states. We don't know, we have the uncertainty about our opponent's cards. So we don't know what is in the stock, what is in and what is in the cards of our opponent. And if we would want to sort of find an optimal strategy, we would have to do this calculation over who wins the game with min-max for all the possible cards in the possible hands. And I think I showed you how to calculate. It was a sort of 5 over 14 or 14 over 5. It was a huge number in any case, in the choices, in the possible belief states that you have per move. So we have an incredibly wide min-max algorithm to start with, would have. So that doesn't work. Similar problem holds with Go. So as far as understood, there were 19 by 19, it's 19 by 19 square. I was reading yesterday, I think there were some 850 moves, possible moves normally in Go. So there somehow this also already ends on the second level, so you will never be able to do a full min-max either. So this is similar problem people in AlphaGo had to deal with and we have to deal with here. We have a big advantage though. Does anybody see the advantage that we have as compared to the AlphaGo? So we have more choices than AlphaGo. In that sense, we're more complex than Go. But what is our big advantage?
Everything is known.
Everything is known? You say no, I don't know what cards my opponent has. In Go, it's known. It's all known.
I meant in Go.
Yeah, okay. But so Go is everything is known, but it's so big that we don't know ahead what happens in 3 moves. Yes, you have a?
You have lower range, so you only got 5 choices at a time. Whereas in Go, you have.
Yeah, we have 5 cards that we can play, but our opponent has then a million choices if we take the uncertainty into account this way. Yeah.
In Go, it's difficult to understand to know the value of a piece at first. Might be very important later on.
Why is it difficult? Sorry, I would say it's difficult to know the value of the position. Yeah, is that what you meant? Yeah, okay. Why is it difficult?
Because in Go, it might be irrelevant at move 5, but it might be important in 80 moves.
Okay. So
It's difficult to estimate.
So what is then the difference between Go and Schnapsen?
In Schnapsen, immediately know if you play a card, you know the points you get if you win the turn.
Okay, so you have some, the one difference is that you have some internal measurements of, so you can have some more local heuristics. But you might have that in Go as well. But I think for me the crucial difference is that I know that every Schnapsen game is maximally 20 moves long. And in Go, usually you make 100 moves and then you still sort of don't know where you stand. So we have a broader tree, but we don't have the length. We always have a restricted length, which makes it, as a sort of a consequence of what you said, or coming back to what you said, makes it easier to estimate our chances of winning. So I think if you have made 100 moves in Go, it's still very difficult to estimate whether you're going to win or not. Yeah? So basically, this problem comes back as a notion of estimating the value of a state. So you go to a state by estimating some moving of cards or some playing of cards. Then you have to estimate how good is this state. And that's far easier in Schnapsen than it is in Go. Still, it might be difficult. So we are looking into that later. So coming back to this, the basis of what we want to do is the min-max algorithm. And that is basically the idea that you find somewhere a value for a node somewhere at the cutoff level, you estimate the utility, and you can back propagate this utility to your root. Now, this is difficult because we can't do this on the full breadth of the tree, and we can't do it on the full depth of the tree. Yeah? And that's exactly the two problems that you also have in Go. So how has it been addressed in Go? This is, so one step back. The way I presented this in the first week was by just doing a random rollout. So random sampling, Monte Carlo random sampling. And that was basically assuming we would know the cards. So we make a random guess for which cards do my opponent have in the RME stock. What would be our strategy to win? Either you can do it informed way, you play the min-max, or in the simple RDeep algorithm, you just do a random choice with a rollout policy of choosing either left or right randomly, and you check how often you win. So one idea could, for example, be to implement RDeep with a random rollout. Oh yeah, and then once you've done this rollout n times, 100 times, and so forth, you just average over how often do I win with a random game and how often do I lose, and then I go for the one where you have the higher chance to win. That is obviously based on the assumption that the game is played randomly. So it might be interesting to say, instead of playing the game randomly, I make a random choice for cards, and then I play the alpha-beta pruned min-max for all the moves, and I check whether I win and how often I win. So it's a sort of two different types of these Monte Carlo sampling bots with two different strategies, and it would, for example, I think, be an interesting final project to look into different strategies for the rollout, whether to apply a simple rollout, a random rollout, or an informed one. That could be interesting. If you just do a random rollout in Go, you have not that much breadth as we have so for Schnapsen, the breadth is the problem, because how do you make a relevant sample over 100,000 possible cards, so distribution of cards? Here we have 800 to start with. We have sort of a little bit of control, even though in the third level we're already far too big, but at least a little bit of control. Here the problem is the depth. And so people developed an algorithm which is called the Monte Carlo tree search, where the tree search through this huge space is informed by the results that you get from randomly played games. So it's a combination of playing those random rollouts and building the tree, the search tree at the same time. And that's the basic idea of AlphaGo. And they have three sort of phases. you make a selection of the node that you're working on next, and that's some utility value that you give to the node. You do a random expansion with a node. You do a random rollouts by simulation. You play a fixed number of games, and then you decide on whether this is a losing state or a winning state, possibly, and then you backpropagate the result to the decision of how you had built your tree, and then in the next step you go back to the original tree that has now been expanded with 1 and update it with new values, and you take the next most promising node in the tree, which might not be the one underneath here, but might be somewhere here now where the values have now been changed according to the values of possibly winning. So basically this is now a combination of these rollouts and the construction of the trees, because we know that we will never be able to build the full tree, so we need to find some kind of representative tree that is promising from a winning the game perspective. And in principle, there are now 2 things that you need to learn for that. Sorry, I would like to take 3 more minutes to finish this, and then we have a normal break, if that's okay. So, but the 2 things that you now need in order to do this rollout, this tree search, Monte Carlo tree search, and that is to estimate how good is a node. So this problem of estimating, am I on a winning side or a losing side? So that's here. Once I do this rollout, I still can't do it until the end of the game, because then already this rollout can be enormously long. So I need somehow to estimate how good is my position that I achieve at a certain point. So I need to have a value to a state, and I need to learn that. And I also need to make a decision on which one to go first. So I'm given a state, and then I need to look at the possible moves that I make, and then I can learn that if I play this card, it's better than if I play the other card. Yeah, do you see the difference between the 2 things that I can learn? The value network, as in AlphaGo it was called, the value network takes as input a state and a rollout and sort of a state, and it estimates how good is this position. So it's like the heuristic values, but now you learn these heuristic values from some games that you play, some rollouts that you do, and from previous games and so forth. So that's the one thing. You train a network that takes as input a state and gives you a value. You are going to win, you're not going to win. The second network that they learned is you're given a state with 5 or how many, in 180, or in our case it would be 5 transitions that you can choose, and the algorithm will tell you this one is the better one. Take the 5th one. And these were 2 types of networks that were used in AlphaGo in order to make the prediction, and together with these Monte Carlo tree search that they built in order to find the right place to do the search in the first place. These were the 3 elements that really made this algorithm so strong and work. So this is then the same idea of expanding your tree in this Monte Carlo tree search by using the information that you get in the evaluation phase from the 2 networks that you've learned, and then combining the results of the value network here and the policy network on the higher level in order to then make the decision that you should make this move. So these were the 3 elements of AlphaGo. And we cannot use all of them, or we don't have to use all of them in Schnapsen, because we don't have this depth problem. So basically we can, if we do the rollout here, at every position we can easily play until the end, either randomly or even with min-max. So we don't need to take care of this, this value network problem, yeah? Because we have an easy way of assigning a value to our nodes in our algorithm. But we still can learn a policy, not network necessarily, but it doesn't matter how we learn it, but we can still, at every place, we can still learn in this tree search that we do, which is the best move to do. And I will talk about this after the break. So let's take a 15 minutes break, start again at 10 past 12.